Okay, here we go. So yeah, I'm just gonna sort of, what do they call it? Learn in public. Let's see what happens. Bum, 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 bum. Okay, so the kinematic equations. So we are asked to look at this graph right here, right? Right, and then under this graph, we have a bunch of squares. That's what essentially we're going to do. Is we are going to sum all of these little squares up. Let's see here. That is very disgusting, very ugly looking, but I think you will get the gist, right? So each one of these sections is delta t, and I believe they label it delta t in, right? And so, boom, boom, right? This little section right here, let's draw that a little bit better. Let's make this a little bit smaller. All right, so that's delta t in, right? And so let's just shade this in to further sort of denote that we're looking at this section right here, right? And so we have these 2 points here. So you can call this t final, t initial, t sub I, t sub f. This is going to be labeled t, right? Uh, and then this is going to be our velocity. V, okay, yeah. So, and then they label this V sub x in average. So we're going to have and calculate the average velocity. Okay. Really, I think I should probably only. Anyways, okay. So first of all, we know that velocity, right? The average velocity equals delta x over delta t. You can also write this dx dt. And so this just denotes the change. So you could say x final minus x initial. Delta t can also be t initial minus t final, right? So you can write it like this if you wanted to. This is really just the calculus shorthand. But there's no really wrong way to do this, right? As long as you come up with the correct answer, you're good to go. So we have the velocity, we have this particle, right? It's moving in a straight line. And so we're going to say that this particle is moving in a straight line, has some velocity. And what it's saying is we're able to calculate its position if we know the velocity, and we're able to calculate the velocity if we know the position, right? It is also possible to find the position of a particle if its velocity is known as a function of time. In calculus, the procedure used to perform this task was referred to either as integration or as finding the antiderivative, right? So I think I wrote, yes, so here, so from this, we can do just some math manipulation, right? So I'm just going to label velocity v. So v equals dx over dt. And what we can do here is we can multiply both sides by dt, right? So those cancel out, and we get v dt equal to dx, right? And then in order to get x, right, the position of this particle, we then need to take the integral of both sides, right? And so it says, suppose the v sub x negative t graph for a particle moving along the x-axis is shown in the figure 2.15. So this figure right here, this is the figure 2.15 out of the book. And so it says, let's divide the time interval tf minus ti into small intervals, which we have done. Maybe I should have done this step by step. Each of duration delta t in, right? And so we've no, these don't look proportional, but imagine they are, right? And so, from the definition of average velocity, we see that the displacement of the particle during any small interval, such as the one shaded in figure 2.15, is given by, okay, so average velocity, we see that the displacement, yeah, so the displacement of this particle can be written as, yes, this change x in equals v, this v x in average times t. They just say t, or they say delta t. Yeah, delta t, so yeah, delta t in, right? So the displacement, so this is the displacement. Yeah, meaning the change in xn, right? So so you have, let's just say, for instance, right, you have this line, right, and your particle can be anywhere, right? So the displacement is right here, xi. This is your displacement, right? Let's just say it started here and it went to here, right? And it did it in this amount of time with this velocity, right? And so, yeah, this is the average velocity in that interval. Therefore, the displacement during this small interval is simply the area of the shaded rectangle. Yes, so the displacement, right, is the area under this, is what they're saying, right? And so that's why we're going to be taking the integral, because the integral is basically giving us an area between some interval, right? And so our interval is going to be tf ti. So yeah. The total displacement for the interval tf minus ti is the sum of the areas. Yeah, so we could also say that the total displacement, right, delta x equals the sum to n. So if we're starting at 0, going to n, right, or 0 to n. Yeah, well, yeah, v x in average delta t in. Right, so this is the area under the rectangle. So essentially what we're doing, we're multiplying these two together and summing up each one. So we're saying, okay, at this point, right, what's the change and what's the velocity? We're multiplying those together and we are adding all of them up, right? So you could say, okay, so the first one is going to be Vx1 average delta t 1, and then say, okay, plus Vx average delta t 2 plus Vx in average delta t in, right? So 2, I guess really you're supposed to do like a plus dot dot dot, dot plus here, plus dot dot plus for I don't know. I think that's just the right notation. So yeah. So we come to that. So it says so this signifies a sum over all the terms. That is over all the values of n. So over each one of these, right? Now, as intervals are made smaller and smaller, the number of terms in the sum increases, and the sum approaches a value equal to the area under the curve and the velocity times graph. Yeah, so if you were to make this delta t in, you would, you would make these smaller, and so you would need more of these rectangles to fill in this area, right? And so essentially what you're trying to do is you're trying to get a better approximation, right? So yeah, what they're saying is delta t goes to zero, right? Doesn't actually go to zero, right? Because then if it's zero, there is no area it's actually getting there. But let's just say, for instance, we'll just go really small, right? We'll say that this length right here is 0.01, I don't know, seconds or something like that, right? And then they're saying, okay, and then Vx goes to what? Goes to, no, n goes to infinity. Yeah. Well, n goes to infinity, right? N's not actually going to reach infinity, um, but it's just a calculus way of saying that we are going to make this infinitesimally small. And so because we're making this infinitesimally small, we need n to be infinite, right? We need to have infinite amount of these delta t's to add up this area, right? and so yeah, this brings up our limit equation, right? So essentially, we're just placing a limit in front of this equation, right? So this becomes delta x equals the limit n going to infinity, right? Oh no, t sub n going to zero, yeah. Delta t n goes to zero, yeah. Uh, and then you sum from in, yeah, and then this is the exact same. This is just v x in average delta t in, right? So yeah, essentially the same thing. It's just sort of trying to denote that we're trying to make smaller delta t's so that we can get a better approximation to what the actual displacement is, right? Because what you can see whenever you're doing it this way, right? Taking these sort of samples, right, of this area, we're gonna be losing a little bit of area as we add these up, right? But what if you were to, yeah. So essentially, what we're doing, right? Same curve, right? Not exactly, but imagine this is the same curve, right? So now we are trying to make these literally just a line, right? Now imagine these are just literally super close to each other, so that you're now you're adding up every little bit, right, without losing any area. Now you still do, right? Unfortunately, um, but there's different ways to integrate and things like that, to get better approximations, right? What you'll learn in physics, and really throughout your career, if you're sort of on this like this path, is that in trying to understand the universe, right, is that through calculation, all we can do is get a decent approximation, right? And so, really, the physicist's job, and the job of people, crunching numbers, is to get as good of approximation as they can to try to fully represent the problem that they're looking at, right? So so yeah, like a decent approximation is not going to matter here, but there's a bunch of let's say in an airplane, right? or going to the moon, right? You want to try to get the closest approximation you can. So your calculations are going, you're going to do your calculations over and over and over again, and make sure that your delta t in is as small as you can make it, and your n is as close to infinity, so that you know for sure that your calculations are super close to what the real value is, and so that you make it to the moon and back just fine, right? But anyways, and so yeah, so what the book says is the limit of the sum shown in equation 2.18 is called a definite integral, and so the displacement of the particle can be written as, yeah. So can be written as an integral, right? So we can write this as, we'll put this here. So delta x equals the integral v dt. And they sort of denote it like this to say that it's a function of time, right? And then of course don't forget your wow, I've been saying it, now I forget it. Your displacement, your interval, right? So we're going from ti, we're going from ti to tf, right? Yes. Always have your final on the top because you're subtracting from here to here, right? So yeah, so where v sub x and t denotes the velocity at any time t, right? So with a function of t, the explicit functional form of v sub xt is known, and the limits are given. The integral can be evaluated, right? So keep that in mind. If the explicit functional form of v sub x and t is known, and the limits are given, so you know the interval, right? Then the integral can be evaluated. And so so now we go into the kinematic equations, right? How can we find other equations through this? Now, so what are the kinematic equations, right? What are we? So kinematics is the I believe it's like the study of change, right? It's the study of right. They don't really have a definition of what kinematics is. Let's see if they have a definition of kinematics in here. We begin our study of physics with the topic of kinematics. In the broad topic, we generally investigate motion. So yeah, kinematics is about the motion of things, right? The motion of objects without regard for interactions with the environment that influence the motion. Motion is what many of the early scientists studied. Early astronomers in Greece, China, the Middle East, and Central America observed the motion of objects in the night sky. Galileo Galilei studied the motion of objects rolling down inclined planes. Isaac Newton pondered the nature of falling objects. From everyday experience, we recognize that motion of an object represents a continuous change in the object's position. Yeah, and so I guess I'll keep reading this. In this chapter, we analyze the motion of an object along a straight line, like the car in the storyline, or the particle, like what we're talking about, right? Because what you learn, right, is that you can neglect a lot of things. So, like for instance, you could easily say this is a car, right? Um, so you can represent a car as a particle, a point in space, right? You don't have to draw the car every time, right? You can just draw a point in space and then draw your kinematic diagram from there. So, anyways, where did we go? Okay, so now we use the defining. So yeah, now we're going to derive the kinematic equations through our calculus. We now use the defining equations for acceleration and velocity to derive two of our kinematic equations, equation 2.13 and 2.16. So let's see. I'm just going to write up on the board what 2.13 and 2.16 are. There's 2.12. Oh, okay. Okay. So this is okay. Okay. So 2.13 is expression enables us to determine an object's velocity at any time t if we know the object's initial velocity and its constant acceleration. So v, x of I, and ax. So acceleration is always denoted by a. Velocity is always v. So this is 2.13 here. So 2.13 is vx x sub f. Vxi plus, I think it's plus a sub xt xt, and then 2.16 x is this equation provides the final position of the particle at time t in terms of the initial position, the initial velocity, and the constant acceleration. Right. So this is x of f equals x I b t plus 1/2 a t squared, right? Yeah, for constant acceleration. Oh yeah, these are all for constant a sub x. So let's just write that for constant. Oh, for constant a sub x. So yeah, what is that saying, right? Constant acceleration. So acceleration, right? So acceleration is equals dv over dt, right? So what we're saying is that the velocity over time is not fluctuating. This is just, you know, let's just say for you're just gonna say a is equal to 1, right? Yes. So this is not fluctuating. It's just a constant value, right? Bum, 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 bum. Okay. So defining equation for acceleration. Okay. Oh, okay. We just did that, right? So okay. So we're gonna start here, right? Bum, bum, bum. I don't know if I want to. I'll erase this stuff. This eraser sucks. Anyways, I wonder if this one's better. Yes. Not so much better. I wonder if this one. Yeah. Okay. Well, whatever. Okay. So defining the equation, right? And so they define basically this. So, but they use um, they denote it with an x, vx dt. Right? I'm guessing because we are still maybe looking at this, right? And we're talking about the acceleration through x, right? Talking about the because yeah, we're talking about this line right here, right? X initial, X final. Well, we're still like just. I'm assuming that's what they're saying. We're still looking at this just straight line. Yeah, we're looking at particles just going in a straight line. Nothing too crazy here just yet, right? And so it says, okay, so with some manipulation, this can be written as, right? So you can do that. You can just multiply both sides by dt, right? And you get a sub x dt Right. I just always like putting the dt at the end. Just makes it easier when you go to do other things with this equation, right? So these cancel out. Um, okay. So you get this equation right here, right? And then what we can do from here is, yeah, okay. So we can take the derivative, or in terms of an integral. Oh, okay. So we're just putting this. Then we put this in terms of an integral, right? So they basically do this. So they put dv of x equals ax dt over here, and then so basically take the integral of both sides. But instead of doing the integral here, or instead of doing that, well, no, I don't think that's even. Yeah. Anyways, so to denote the displacement of the velocity, right, the change in velocity, we write Vx initial, or is it, yeah, final minus initial, minus Vxi equals this right here, right? Yes. Oh, and then of course you can't forget your interval, right? So we're going, I don't know why this is going from final to initial, but this is, yeah, I mean, you can easily say from 0 to t, right? Because your initial value, 0 to t. I mean, yeah, this is essentially tf or ti. We're saying our initial is 0 for some reason. Huh. I'm wondering if it's because for an acceleration, I don't know. Yeah, why are we saying? For the specification in which the acceleration is constant, x to be removed from the integral to give, f x can be removed. Oh, okay, yeah, yeah. So because a is a constant, right? We can essentially move it out here. Right. Well, I won't bother with that for now. And so let me say this, right? Then this is essentially, so when you're taking the, so you can basically say, okay, there's a 1 right here, right? And the integral of 1 is just t, right? And so, yeah, so this is a sub x of t from the integral 0 to t, right? And then from here, basically, yeah, t minus, yeah, t minus 0, right? And then this just equals a sub xt. I guess maybe I should really make sure to really put the emphasis that that's an x there. Sub. Okay. Okay. So yeah, we need to remember the a sub x, the acceleration is constant. Right. Okay. And so now we know that, which is equation 2.13. Oh, yeah. So yeah, they're basically saying this is equation 2.13, right? So it's here. Let's write Vx of f minus Vx of I equals, okay. Uh, and so what you can do is you can just add Vx of I to give you Vx of f equals Vx sub I plus a xt, right? And that's 2.13. Yeah. So just simple arithmetic, adding that to the other side gives us that equation, right? So that's how we get 2.13. Yeah, cool. Okay, so now let's find the other one, right? So erase this. Okay, so we start off with the equation Vx equals dx over t. Vx equals dx over dt, right? And so yeah, we do the same thing that we do there. Basically, multiply both sides by dt, right? Just a double check. Yeah, so multiply both sides by dt, right? Now you don't have to do this step, but for the learning purposes, I think you should make sure and do this every time. Okay, so dx equals vx dt, right? And then, so I'm guessing they want us to take the integral again. Yes, yes. And so they say, okay, well, so I'm guessing they're saying that the velocity is fixed as well, right? We're saying that that's constant. Oh, yeah, yeah, yeah. We're saying that the acceleration is constant. This is the acceleration, or essentially. Hmm. Well, we're saying that a of x is constant. We're not saying that. Okay. Anyways. Hmm. Okay, let's. Okay. Okay, so again, we can write this sort of like what we did over here. We can say xf minus xi equals, and then we need to take this integral, right? So from 0 to t, vx dt, right? Okay. Aha. Okay, so what they're saying is vx equals this, right? Is that what they're saying? Yes. Okay. So let me do. Now we take this and plug it in here, right? So we get xf minus xi um, dt, right? Okay. So you can also write this vx dt plus. Oh, we're gonna get this again. How do they? Yep. I'm. Oh, but they say this is, yeah, of course, yeah, this is xi, right? Not xf, right? Okay. Yeah, so you can also write this as this. So, right, and we know what this is, right? Yes, this equals vxi t, right? Oh, wait a second. Can we? No, it's equal to. It's just equal to axt. Axt. Let's just do the integral, right? So we can pull out. Yes, yes, yeah. So we can pull out the ax. Yeah, sorry. We can pull out the ax 0 to t. We have t dt. This integral, we're just going to focus on this side right at the moment, right? This is t squared over 2, right, from 0 to t. So then that gives us, so what you could do is t squared over 2 minus 0 over t, right? And then that just equals t squared over 2, since that's 0, right? And of course, a x in front of it. Okay, and v, is that going to be just, Yes. Yeah. Yeah. And so this becomes x I t. I need to better denote these x I t, right? And then that's from 0 to t. And so that gives us vxi t. Okay, so plus ax. Okay, t plus ax. And then this gives us t equal to xf minus xi. So then we can say, okay, well, sort of running out of room here, huh? Well, then I'll just write it over here, I guess. Um, yeah. So this just equals okay. So the final position, if you know the initial position and you know the initial velocity, and you know the acceleration, then you can find the final position. Oh, okay. Well, yeah, just that equation right there, 2.16. So, yeah, I believe that's it. And so, yeah, we've derived 2.13 and 2.16 using calculus. Not too bad, right? So, yeah, if you have any questions, feel free to um, leave a comment, and I'll try to answer them the best I can. Thank you.